research to inform passage spacing for migratory amphibians and to evaluate efficacy and designs for elevated road segment passages. And there's a number of people that have contributed to this from the USGS and Forest Service and other partners. So our objectives is to really understand the spacing of underpasses, inform the spacing of underpasses for migratory amphibians using Yosemite toad as one of our study species. We wanted to look at the effectiveness of barrier fencing as far as the opacity. Does it matter if you use solid fencing versus mesh fencing? And also the effectiveness of a prototype elevated road segment passage for Yosemite toads and other small mammals. And then finally, I'll be presenting designs for primary roads, for these systems for primary roads and highways. Okay, so here's the Yosemite toad. They are federally threatened. They are a high elevation, long-lived amphibian that moves up to 1 kilometer or more to annually migrate between breeding and upland habitats. They move straight line distances to breeding ponds in the spring while there is still snow on the ground, as you can see. And then they return to the uplands typically throughout the rest of the spring and summer. And this occurs during rain events. I'll let you see them make it to the water. So the study area was in the Sierra National Forest, California, where large numbers of Yosemite toads were getting killed on a Forest Service road adjacent to a breeding meadow. So when the Forest Service came to us to ask us for a solution to the high toad mortality in 2017, we quickly realized that there's only one tool in the toolbox, which were microtunnels with barrier fencing. So, but however, there was some recent evidence starting to come out that showed that these mitigation systems could be barriers to movement and could potentially be worse than the road mortality problem itself. Why is this? What we're calling this is the filter effect, and it can be due to multiple things, including low passage permeability if they're not readily using these small tunnels, as well as new evidence showing that migratory amphibians may give up along the fence line if they don't readily find a passage. And to explain this better, I'm going to describe a study we conducted and published on the behavior of the California tiger salamanders when encountering a road barrier fence. And we had also tested transparent mesh fencing versus solid fencing there. So the figure on the left is the average move distance. It's basically a distribution of move distance of individuals of California tiger salamanders that made contact with a road barrier fence. And then the figures on the right are the probability that a tiger salamander would reach an underpass based upon the distance from the underpass where they encountered the fence. And the toward versus away is when they actually came into contact with the fence. Did they turn left toward the underpass or right away from the underpass? So the results in this study showed that although these tiger salamanders move, up to 1,800 meters from uplands to breeding ponds, they only moved an average of 40 meters along a road barrier fence before giving up and going back into the habitat, thus not breeding. Most of these movements were salamanders moving back and forth along this distance of fence. So it wasn't just a single pass by the fence and go back into the habitat. They moved back and forth, trying to go forward. And as you can see from the figures on the right, the direction choice of the salamanders when encountering a fence had a big impact on success. Individuals that initially turned toward the underpass were much more likely to reach a passage than those that turned in the wrong direction. Solid fencing also showed better results than mesh fencing that they could see through. Similarly, Ottberg and Vandergrift in 2019 found that the common toads in the Netherlands only gave up after an average of 40 meters, exactly the same, even though their migration distances go up to 1,600 meters. So basically, both of these species move less than 10% of their migration distances. And it's really unknown why, but these amphibians move straight line distance to their breeding habitat, and we theorize it may be related to their long versus short distance orientation mechanisms that they use to move toward the breeding pond. And I can talk about that later if you like. And also, although 40 meters was the average movement distance, in order to promote a 90% permeability to the population, we recommended passage spacing of approximately 12.5 meters or less. Yes, using a 90% tolerance interval for the distribution of movement distances. So I hope that made a little bit of sense. And so that's just kind of a prelude to the study that I'm going to be talking about now. Going back to mitigation possibilities, when the Forest Service came to ask us for a solution to the high toad mortality in 2017, we quickly realized that, you know, there was the one tool in the toolbox, but it didn't really seem feasible given the topography of the eroded area, and it would have required considerable excavation in the adjacent sensitive habitat. We decided to kind of think outside the box and try something new. And in collaboration with Stephanie Barnes of the U.S. Forest Service and Anthony Composites, we designed an elevated low bridge passage that can be set on top of an existing road that we call an elevated road segment. And the prototype for the Sierras was 100 feet long with an 8-inch high passage made from road mats that are used for construction projects in sensitive habitats. And there's just a little short video of it being installed on the Forest Service road. And here are some photos that show from a side view, and then the one on the lower right is looking underneath the passage. It's, like I said, 8 inches high and permeable to sunlight and rain. And that was just installation. So on each side of that ERS passage, we built 120 meters of barrier fencing for the barrier fence study, the movement distance study. You can see we have solid fencing there on the top and then mesh fencing on the bottom. And that was actually a Yosemite toad looking through that mesh fence. He was not happy we put it there. All right, and this slide shows the study design that we used to inform both the fence movement distances for Yosemite toads and the effectiveness of the new passage. We used active infrared cameras for monitoring movements along the 120 meters of barrier fencing on both sides. So those are represented by these circles here in different colors, would all be cameras. You can see that some of the cameras are actually in the forest, which are green. And then we have some cameras here in the adjacent habitat. It's just the roadside habitat. So it doesn't have that tree cover and leaf litter. It's more open. So we kind of looked at that separately. And then the red cameras here are under the actual ERS structure. And because it was so wide and the cameras are quite expensive, we weren't able to put cameras across the entire structure. So we basically subsampled where we thought most animals would be coming in. And then down here, we had some Reconyx cameras taking time-lapse photos every 5 minutes, also trying to, get information on animals that are passing through. So individual identification of the toads was done using a specialized pattern recognition software. As you can see here, that and each toad has a completely different pattern, so we can identify them individually, and that's how we know how far they travel and where they're going. And unfortunately, due to the low height of the passage, the the individuals that were moving under the passage, we couldn't get that top-down view. So there we could identify species, but not individuals. The results for the individual movement were, we documented 42 Yosemite toads along the fence line over the entire study. And most were in the first year of the study, and then a really bad series of events, including extreme drought, a fire that went all the way up to the elevated road segment, and forest clearing that was done associated with this at the site, likely contributed to low numbers in the very last years. So, but we did get a pretty good distribution. We got 24 on the mesh side and 16 on the solid side. We had a mixture of 24 subadults and 18 adults. And we actually got an average give up distance of 46 meters with a median of 40 meters, which is really amazing how close that is with the other species that have been studied. Typically they had multiple direction changes. We detected a total of 29 individuals that actually moved under the ERS, but because of our subsampling and not in time and space, we estimate that at least 100 went under the ERS. Yosemite toad adults moved farther along the solid fencing than the mesh fencing. We only had 6 adults on the solid side, but they averaged 80 meters along the fencing versus 30 meters along the mesh. And then subadults were 40 to 50 meters. So this slide, similar to the previous one I showed, shows the movement distance distribution for Yosemite toads and their probability of reaching an underpass based upon the distance from the underpass where they initially encounter a fence. And results were quite similar to migrating CTS and common toads in the Netherlands as far as the average movement distance goes. And you can see here, same pattern with a much greater probability of finding a passage if they initially turn toward versus away from the passage, and a higher probability of reaching the passage when using solid versus mesh fencing. And so looking at the 90% tolerance intervals, if we want 90% of the population to be able to move under passages for passage spacing decisions for future projects, we're recommending passage spacing of 20 meters or less. Here's just some videos that you can see the toad moving along the fence. Actually, it's going over this halt active trigger, which is a really good camera improvement for detecting these species, which don't work very well with the passive infrared cameras that we're used to, the game cameras. Look in the top right here. This is where the toad is moving into the passage. And there's a couple more. I'll try to get some better video. This was some video that we got in the first year. There's another one you can see. That's just a different orientation from the other side. And then we also got many other species. This is a rubber boa and a whip snake. This is a whiptail lizard. Hopefully you can see it. This is a Pacific tree frog. And a wood rat. This is all under the ERS structure. Tree squirrel, chipmunk, pine marten, spotted skunk, and even a marmot. Cool. So now to the larger community and effectiveness of the ERS passage for that larger community. Here again, we're looking at relative activity of amphibians. These are the amphibian species here, and mammal species here, reptile species here, and we're looking at relative activity of those in the forest versus immediately adjacent to the ERS, that more open habitat I talked about, and then the red being under the ERS. So in analyzing the relative activity, there were really no significant differences among activity among the different locations. 20 small animal species that were detected in the forest habitat were also detected under the ERS structure. 2 with very low sample sizes of 1 and 11 mammals were not detected under the ERS. That was the broad-footed mole and the northern flying squirrel, which we don't really expect to be under there anyway. And overall, amphibian activity trended slightly lower under the structure versus in the adjacent forest habitat, just by a little bit. And then with mammals, it was kind of the opposite. They were more active under the structure than in the adjacent habitat. And then with reptiles, it was overall slightly less, but it was mixed by species. But still no significant differences. And this is just a way to look at their activity kind of in a spatially explicit way. So, here again, you can see the green. This is like along the fence in the forest. This portion here in the middle, which is supposed to be brick red, is right under the ERS. And then the orange sections are right next to the ERS. And then this is the forest habitat. So you can see that the Pacific tree frog is really active here. There was a lot of amphibian activity in this portion of the forest. And there really is no difference between under passage use versus that adjacent to the passage. And kind of similar results with the reptiles. And we actually think that, I think that to even further increase, their use of the passage, we could increase cover, like leading up to the passage. I think that would be helpful, and that could be from downwood, leaf litter, or vegetation. Also, the passage doesn't have a natural soil bottom because it's on top of a road, but that's part of what makes it really nice and easy, but that could potentially also increase activity under. So small mammals often trended higher under the ERS, and Stephanie thought that is because they were having regular parties under the bridge. But we think it might be due to that there's just so much more increased protection from aerial predators. So, major predators of small mammals and also larger animals can't get under there. So it's definitely a nice, safe place for them to be. Okay, so the conclusions of this part is that really, I said 12.5, here I say 10 to 20 meters between passages are currently supported by science for migratory amphibians, so to inform passage spacing. Current literature indicates that wider passages are more permeable to movement of many amphibian species. So, and then we've just shown that the ERS is highly permeable to small animal movement. And just some considerations. It has a potential to better maintain connectivity over large road spans with widespread mortality because it can theoretically be built to any length. Permeable to rain and light, incorporating moisture during rain events and natural conditions within the passage. So rain events is when they're moving, that's when the ground is wet, that's, they're amphibians, that's what they like. No effect on drainage. So, if you have to excavate and change water flow, this has no effect on that. So the passage is also less prone to flooding at the natural grade. No damage to adjacent habitat, has a small area of impact. And it also eliminates or reduces the need for barrier fencing and associated maintenance with regard to fencing. And at least this prototype is removable. So it could actually be, set up during a season and then removed and, you know, do something like that on an annual basis. Here are just some photos that show that there were very large vehicles going over this on a regular basis, and that included recreational vehicles, logging trucks, fire trucks, as well as motorbikes and bicyclists. And, we were told by Anthony Composites that this design could be built to meet many county and city road standards. Okay, but this doesn't meet the criteria for a lot of DOTs and higher volume roads. And so we really wanted to adapt this ERS prototype to high volume roads that would meet AASHTO standards, would also be permeable to light and moisture, uh, have a natural soil bottom. We were looking at potentially a 1 foot passage height, and that would be safe for vehicles and bicycles. So we worked with Docken Engineering to come up with 4 concept designs to meet these requirements, and all incorporate Caltrans bike safe grates along the passages to provide natural light and moisture, as well as, hey, no laughing, as well as vehicle safety guardrails. 2 are low bridge designs up to 70 feet for each span, using both longitudinal versus transverse precast girders. And the longitudinal designs support stage construction and also reduce noise from vehicles moving over the grates. These are these 2. The 2 on the bottom are basically repeating passages along a raised filled road, and using either precast culverts for the passages or precast abutments. So for the portions that are between passages, smooth barrier walls are incorporated into the side of the raised road, with overhangs to prevent reptiles and amphibians from getting up onto the road. And then here's just some renderings. That's the longitudinal precast girder, kind of bridge concept, low bridge concept. There's the transverse precast girder. So there's the wetness across the entire length. Repeating elevated precast box culverts. And we used for this design a standard of a 5 feet wide. And then there's the rendering for repeating elevated precast abutments with short span metal grates, which would be specially made. And then for cost considerations, so further features, advantages, and disadvantages are all described in the report. But here are just some relative costs to install 100 linear feet of a 14-foot wide elevated road type structure, like for a 2-lane road, for instance. So here, if we're just looking at the 14-foot wide, and this includes everything, installation would be about $47,000. And then if we actually go to a bridge structure, they're really expensive. So that is like 10 times more, about 500,000 per 100 linear square feet. And then if we go to the repeating culvert, short span structures with 10-meter spacing, it would be 150,000 per 100 linear feet. And with 20-meter spacing of passages would be more about like $100,000 per 100 linear feet. And these costs include the costs of raising the roadway, traffic handling, drainage, etc. So all of the different things that need to be done. So considerations on when these would, apply, especially areas with challenging topography where it's difficult to excavate down to do something, to create a tunnel, uh, or repeating tunnel, uh, and where you don't want to alterate drainage patterns, if there's property constraints. Also, considering the no need for fence maintenance as long-term costs that have been discussed. Things that can save costs are things like stage construction, accelerated bridge construction, uh, and also if you use a smaller culvert, like I said, we were designing it for 5 feet wide, potential depending upon the width of the passage, a 4 foot wide one might be just fine. Also, reduce height for the precast abutment. And if there is some potential for grading so that it doesn't need to be raised as high, that would also have some cost savings. So final takeaways: passage systems for migratory species should consider the filtering effect of the barrier fencing and the give up distances so that the mitigation solutions can both reduce mortality and increase connectivity. The elevated road segment designs can provide another alternative to provide high permeability to movement for migratory amphibians and other species. And there's many design options available depending upon road characteristics and site-specific considerations. So we thank the Transportation Pooled Fund partners for helping to fund this work and many other partners. Thank you.